Today we will discuss how to realize any logic gate using universal gates. NAND and NOR are the universal gate. The meaning is any Boolean function or logic gate can be realized using these two gates. So first we will learn how we can realize NOT gate using NAND gate. This is the symbol for NAND, NOT gate. That means you give input A, you will get output A bar, complementary. This is my NAND gate. NAND gate is two function and two input function and one output function device. However, our NOT gate is one input and one output. So how to realize this function using NAND gate? By combining these two inputs, we have the single input A, which is equivalent to inverter input, and then what the output I get here, it is just the NOT gate. The output I can write in the form from the NAND gate, it is equal to NOT of A and B. We can verify the truth table of NOT gate by putting the different values of A. For example, if I put A is equal to 0, then from here we will get A 0 and 0 means 0 and NOT of 0 is 1. That is, my output is inverted value of what I applied as A on input 0. In the same manner, we can also realize NOT function using NOR gate. NOR gate is again two input and one output device. Now by combining these two inputs, we have single input which is required to realize NOT gate. Here we can write the output in the form NOT A or A, which is this gate. Now we can check the truth table again. Suppose A is equal to 1. A or A means 1 or 1, that is 1, and NOT of 1 is 0. So again it verifies the truth table of inverter, because if I apply 1 on input, I will get the output 0. This means that NAND and NOR can be realized to implement NOT gate. In the similar fashion, we can design or we can implement other basic Boolean functions using NAND and NOR gate. For example, the OR gate using NAND gate. That this is the truth table of OR gate. For one combination 0 0, the output is 0. For other cases 0 1, 1 0 or 1 1, the output is 1. Now I want to implement this truth table, which is OR gate truth table, using NAND. So I need two input A and B. For that, two NAND gates are used and their two inputs are joined and giving me one input A. Similarly, in this NAND gate, again two inputs are joined and we get another input B. The output is again going to one more NAND gate, and which gives me output Y. So if I want to write my Y function in terms of Boolean is, it is having two input, one coming from this branch, that is NOT of A and A, another is coming from this branch, that is NOT of B and B, and it is ending here, so this AND is here, and finally because of this bubble we put NOT outside. Now we will verify the OR truth table by putting inputs combination here in this expression. For example, if I take A is equal to 0, B is equal to 0, that means A 0 is applied to this gate and 0 is applied to this gate. What will be the output Y? So here A and A, that is 0 and 0, and here again B is also 0, so 0 and 0. This will result in NOT of 0 and this will result in NOT of 0. NOT of 0 is 1 and NOT of 0 is 1 again. So 1 and 1 means 1 and NOT of 1 is 0. That means if I apply A is equal to 0, B is equal to 0, my output should be 0, which also verifies the truth table here. A 0, B 0, Y 0. In similar fashion, we can apply the different combinations on A and B, like A is 1, B is 0, B is 1, A is 0, and B is 1 and A is 1, and we can verify the remaining truth table components. AND gate using NOR gate. This is truth table for AND. For all combinations of A and B input, we have the 0 except that when both the inputs are 1, 1. Now we will implement this table using NOR gate. So to get the input A and B, again 2 input NOR is used, and by joining these 2 input we have a variable A. Similarly, by joining another 2 inputs of other NOR gate, we have input B, and these 2 inputs are going to another NOR gate, and we have the Y. If we backtrace the Y function from A to B, the Y can be written as, it is having 2 input, one coming from this NOR branch, another is coming from this NOR branch. So first input is not A or B, which is this, and second is not B or B, which is from this. It is again NOR gate, so ORing function is here, and this bubble is shown here not. Now by giving some input values, we will try to verify our truth table. For example, A is equal to 1 and B is equal to 1 is applied to this circuitry. Here we have not 1 or 1, that is A or A, and here we have not 1 or 1, that is B or B. 1 or 1 is 1. Similarly, 1 or 1 is here 1. Not of 1 or, which is as such here, not 1. Not of 1 is 0, or is 0. 0 or 0 is 0, and not of 0 is 1. That means if I apply A is equal to 1 and B is equal to 1, the Y is 1, which verifies the entry of this truth table that A is 1, B is 1, output is 1. We can prove that there is an equivalence relationship between the gates. For example, a NAND gate is equivalent to inverted input OR gate. For example, this is NAND gate. Its output is equal to AB bar if A is applied here and B is applied here. This gate output is equivalent to if we invert the input and apply this input to a OR gate. So A will be here, that means A bar, B bar, which is equal to AB bar, that is my NAND output. So Boolean form we can write AB bar is equal to A bar plus B bar, which is coming from this gate. If we want to verify this relationship, we apply 0 0 on NAND gate. So its output is 1 and inverted value of AB, that is 0 0, is inverted to 1 and 1, which is applied on this gate. So 1 1 and ORing. So 1 1 ORing is 1. That means the output which I am getting at NAND gate is equal to the output which I am getting inverted input OR gate. It shows that a NAND gate is equivalent to inverted input OR gate. In the similar fashion, a AND gate is equivalent to inverted input NOR gate. So AND gate output is A dot B and inverted input NOR gate output is A bar plus B bar, which is equal to A B. A NOR gate is equivalent to inverted input AND gate. This is NOR gate, and if we invert the inputs and apply to the AND gate, we will get the same functionality as we are getting here after NOR gate. In Boolean form, we can write A plus B bar is equal to A bar B bar. An OR gate is equal to inverted input NAND gate. This is OR gate. Its output is A plus B. And here we are having inverted inputs and apply to again NAND gate, which is A bar dot B bar. So A bar dot B bar is equal to A plus B. By applying different values, we can check the outputs values.